Let's look at it an example that we started with last lecture. So there we had the sequence x of n is just 1, 2, 3, 4. Just consisted of 4 samples, so capital N here would be 4. And then we actually went through and computed by hand a couple of these, the DFT of a couple points. And we had x of 0 is equal to 10, x of 1 is minus 2 plus j2, x of 2 turned out to be minus 2, and x of 3 turned out to be minus 2 minus j2. And we verified that using the octaves FFT function. Now, in polar form, we could write this as 10 at angle 0. This would become 2 square root of 2, and that angle is actually 135 degrees, negative 2 over, and plus 2 up. So that would be, it's not negative, it's actually positive 135 degrees. Negative 2 would be 2 at either plus 180 or minus 180. Plus 180 seems to be the convention. And then the final one would be negative 2 over and negative 2 down. That's the one that's actually at minus negative 235. Negative 135, excuse me. So this would be the DFT expressed in polar form. And so our amplitude spectra would consist of, remember, it was the magnitude of our DFT divided by n, so 1 over 4, and then simply 10, 2 square root of 2. I'm just taking the magnitude of each of these. Of course, I could go back to the original rectangular form, and this would be square root of 2 squared plus 2 squared, which is 2 square root of 2. The magnitude of this is just 2. Then this has the same magnitude as the second element in the array, so 2 square root of 2. This would be 5 halves, 10 divided by 4, square root of 2 over 2, 1 half, and then square root of 2 over 2. Okay, and then certainly the phase spectra I can get immediately by expressing the DFT in polar form would be 0 degrees, 135 degrees, 180 degrees, and then minus 135 degrees. And then the power spectra is just the AK squared. So it'd be 5 halves squared, or 25 over 4, so that's 6.25. And then square root of 2 over 2 squared is going to be 2 over 4, or 1 half. And then 1 half squared would be 1/4. And then this is going to be a half again. So this would be the amplitude, phase spectra, and power spectra. Now, we can, if you plotted the amplitude spectra, and again, these are all going to be real, so we could plot each of these. So, the amplitude spectra, if I wanted to plot it, 4, 2, 1. So in K, the indexes would be 0, 1, 2, 3. This would be K. And let's say 3, 2, 1, 1, 2, 3. The first element here, 5 halves, is going to be 2.5. And if I do a stem plot, that would be at 0. Square root of 2 over 2, that's going to be 1 over 1.414, 0.707. So that's actually going to be less than 1 here. That would be this element. And then the next element is going to be 0.5, so it's going to be about right there. And then the third element would have the same magnitude, about 0.7. So it's going to have the same amplitude as x of 1, x of 3, and x of 1. Actually, a of 3 and a of 1, because these are my A of k, this is my amplitude spectrum, a plot of that. And again, the value of this versus working with x of k directly is that A of k is, they're all real values, so I can actually plot them. They're really, related directly to the magnitude of x of k. And then I could also plot the phase angle or even the power spectra similarly. Now this is really easy to do in Octave. So it's incredibly easy to do. So I'll give you the Octave code here. We could define our x vector quite easily as just 1, 2, 3, 4. I could define n as just the length of x. Of course, it is just 4, so I could just set it equal to 4. And I can get my f of t then, or my DFT of my sequence using the f of t algorithm. So this is the lowercase x, and this is an uppercase x. And I could calculate my then amplitude spectra. It's going to be the absolute value of capital X divided by n. And this would give me a vector of 4 components. Similarly, I could even calculate the power spectra is going to be the amplitude spectra squared. Again, I want to square element by element there, not do a matrix multiplication squaring. And the phase angle I could simply get as if I do the angle of x, I'll get the angle in radians. I can use the rad to degree function to convert those angles of my capital X vector to degrees. Okay, and this would be a 4-element vector containing these 4 phase angles actually. If I wanted to plot, let's say the amplitude spectrum, I could do it just as a stem plot versus k. I could also plot it versus frequency. Now up here on this plot, if I wanted to do this versus frequency, let's say the sampling frequency here is 10 hertz. I think that's what I've used in the past with this example. So the bin separation, f of k, would be f of s over n, which is 4, or 2.5 hertz here. So in terms of, actually this would be frequency, yeah, frequency here. So let me try to erase that. This would be f in hertz. This would be f of s. This would be 10. This would on k. This would be n. And then these would be 0, 2.5, 5 hertz, and 7.5 hertz components. Okay, so if I could easily plot versus k, I could just do a stem plot of, I could form my k vector going from 0 to n minus 1. And then I could just do stem of k and then a. And it'll produce a plot very similar to the one up here. If I wanted to do it in terms of frequency, plot like in frequency, I'd have to form my frequency vector. Looks like I don't have f of s defined in this script. So I could define f of s equal to 10. And then I could define my frequency vector. And it's going to be my k vector times f of s divided by n. So now this would be a 4-element vector. And so I could actually do this plot versus frequency as stem of f versus k. And then get a plot like this versus with frequency values along my x-axis. Similarly, instead of a, I could do P here for my power spectra, or phi here to get my phase angle spectra. And we'll continue this lecture in the next video.